Okay, question on Wiley on 3.1. 3.1. What problem? 27. 27 has an error. If you have the point, I think 2, 1, and you get minus 2 over 11, and then in Wiley counts it wrong, and if you show solution, it's actually the right solution. So if you go through and do it correctly, Wiley is attempting to fix their coding error. So they also had a problem on how I can submit errors. So a student emailed me and said, I have this right, Wiley counted it wrong. I go in there and see that. So then I submitted the error, and you get this little, it's kind of italic. I don't know if you can see that very well, but it's in italic. And then you get this warning saying that there's a possible problem with this, there's a possible issue with this problem. Go ahead and do it. If you're wrong, if Wiley counts you wrong and you're correct, by the time they fix it, they go back and rescore everyone, so you get your points back. If you do it right, I mean, if you want to send me an email, I can go in there and give you your points back. Wiley will eventually get there, though. So is your question on how to do it, or I put in the wrong answer?
I put in the right answer.
Yeah, I put in the right answer and it counted it wrong. So yeah, so if you put in the right answer and you counted it wrong, just give it some time. It should be fixed. Question?
Can you do number 1? I kept getting it wrong.
Okay, so let's look at it. So it wants you to differentiate this implicitly, express your answer both in terms of x and y. And then solve the equation for y and differentiate it. So this function will only be a function of x, and then show how they're the same, which you're going to put the same thing in here as you do in here. So let's look at this problem. This is number 1 on 3.1. So you have x plus x times y minus 6x to the 6th power equals 4. So they want us to do implicit differentiation. Implicit differentiation, I differentiate the whole relationship with respect to x. So what's the derivative of x? 1. What's the derivative of x times y with respect to x? I have to do the product rule, right? So the derivative of x is 1, hold y, plus the derivative of y, hold x, and I get x times dy dx. Does anyone have any questions with that? What's the derivative of 6x to the 6th power? What's the derivative of 4? 0. Right? So now at this point I want to solve for dy dx. So rearranging, I have x times dy dx equals 36x to the 5th minus 1 minus y. So I move everything else from the right hand.
Plus 36x.
Yes. Or here. This is a minus, but then I add it to the other side. Sorry. It's a little small. So solving for dy dx, I get 3x to the 5th minus 1 minus y over x. You should be able to enter it like this. You could also simplify it 36x to the 4th minus x to the minus 1 times x to the minus 1 times y, but there's no need to do that. Wiley should accept this. Question?
Silly question. I think you've explained those 3 dots before, but what's
It's just a little thing I say. It's like a conclusion. It's
Therefore.
like, therefore, yeah. In math, there's a lot of like, this is for all. This is, and I don't remember this. There's a lot of different notations. So for every x greater than, some delta, there exists. That's what that is. There exists. There might exist a lambda greater than epsilon. So these are just different ways to say for all x greater than delta, there exists a lambda greater than epsilon. this is a kind of a conclusion thing. When we go to prove things, which if you ever taken a proof class, a lot of times this just means like a conclusion.
Okay.
I just use it sometimes. I don't. Yeah. So basically, I'm saying this is where I wanted to get to. This is my conclusion that this is the derivative. So that's what you would put in. Yeah.
I don't know why you did that.
Yeah. Just picked up from some class I took. So does that make sense? Did you get that? Okay. So now, if I solve for y in this equation, I have y equals 4 plus 6x to the 6 minus x over x. If I did that correctly. Right? So I could rewrite y as 4x to the minus 1 plus 6x to the 5th minus 1. Now dy dx would equal minus 4x to the minus 2 plus 30x to the 4th. So I want to show if I plug in y to this expression, that this expression should equal this expression. So doing that, I have, see, dy over dx equals 36x to the 5th minus 1 minus the quantity 4 plus 6x to the 6 minus x over x all over x. So I've got some cleaning up to do. Maybe I'll write it as 36x to the 5th minus 1 minus 4x to the minus 1 minus 6x to the 5th plus 1 all over x. So cleaning it up a little more, I have 36x to the 5th minus x to the 5th over x. So it would be 30x to the 4th. The minus 1 and the plus 1 cancel, and then I have minus 4x to the minus 2nd. Which equals what my original function, right? dy over dx. So your first box you're going to put this in, and then your second box you'll put this in, and the third box you'll put this in. It'll be the same thing. It doesn't matter the order there. Does that make sense? So I did implicit differentiation and I got a derivative, but it had an x and a y in it. Then I solved for y as just a function of x and just did regular differentiation. And then I said, okay, I got y as a function of x. I can plug that back in to what y is in terms of x and simplify it and show that dy dx is the same thing as dy dx over here. The two different techniques give me the same answer.
So do we have the choice of which way to do it?
It depends on the directions. If it says use implicit differentiation, you can get to here. If it says differentiate it, you have your choice if you want to do implicit differentiation. But implicit differentiation is quite a bit longer because you have to solve for y anyways, plug it back in and simplify.
So we can also use quotient rule.
Here, yes, you could use the quotient rule, but the power rule is so much easier than the quotient rule, right? Some of you are maybe not. So if I can write x as to a power, it's so much easier to do that than the quotient rule. But yes, you could use the quotient rule here. Make sense? Any other questions on Wiley? Okay, so today we're going to cover 3.3. Oh, I already had it up, so I want to pull this up for a minute. And 3.3 is getting into derivatives of inverse and inverse trigonometric functions. So we'll learn the derivative of sine inverse, cosine inverse, tangent inverse, and the remaining three. So one thing your book does that the first time I taught this confused students, and the second time I taught it confused them even more. So hopefully I can explain something before I get started, and then it won't confuse you guys too much. So we're going to find the inverse. We're going to find the derivative of an inverse function. So at the beginning of calculus, I had you find what the inverse function was, right? So if I gave you a function, you could find the inverse. So if I wanted to know the derivative of the inverse, you could just differentiate that function, because you guys can differentiate many functions now. However, it's not always possible to even solve for the inverse. So you can use the information about the original function to find the derivative of the inverse function without actually finding the formula for the inverse function. So some things about the inverse. So the red function here is the original function. The blue is the inverse, right? But the red could be the inverse of the blue function, right? Because the inverses mean they switch back and forth. If I plug in 2 into the original function, I get out 1. That means I plug 1 into the inverse, I get out 2. So this point would be x comma y. This point would be y comma x, right? So maybe x and y gives you some notation of what that means. So you might call it a, b. So if I plug in a here and get out b, I plug b into the inverse, I get out a. So a lot of times we used to see y as a function of x. In this section, your book's going to write x is a function of y. So then they can find dy dx is the derivative of the inverse. So don't get too caught up on what x means and what y means. They're just placeholders for plugging into one function and getting out something else. So if I plug a into my function and get out b, that means if I plug b into my inverse, I get out a. That's the relationship. It also turns out that these two relationships of the slopes are related. However, this is a slope at 2, and the relationship is going to be the slope at 1. Because the point 1, 2 is paired up with the point 2, 1, right? So if I talk about the slope at 2 of the original function, I can figure out what the slope is at 1. So I have to be really careful on what I'm plugging into my function. Okay, so let's start writing some of these stuff up, and then I can do some examples. And I'll actually go over this example, but and I'll show you it. So it's 3.3. So we're going to find the derivatives of exponential and inverse trigonometric functions. Okay, so let's say I want to find the derivative with respect to x of f inverse of x. Be very careful. I'm really bad at writing like the derivative of the inverse. A lot of times making this would be the derivative of the inverse of x prime. Your book will write it like this. What do they do? They do it, let me see what they do really quick. Oh yeah. So then they do this. But can you see how that can get confusing on what that is? Especially when if you're kind of sloppy the way you write the inverse in the derivative. I typically will write it like this. Your book does it like that a lot, but don't get too caught up on that. So this is just saying the derivative of the inverse. So it turns out we had this formula, right? We had this picture from the book. We had this was 2 comma 1, so this is the function. This is the line y equals x, right? Because inverse functions are reflected about the line y equals x. So if this is 2, 1, then the corresponding point, if I plug in 2, I get out 1. It means I plug 1 into the inverse function, I get out 2. So I want to find the inverse of, I want to find the derivative of this function. But I have no clue what that function is. So I'm going to name it something. Your book conveniently names it x. I don't know why. So they have, let's say x equals f inverse of y, and y equals f of x. Right? So what it's saying, if I plug in x to my function, I get out y. If I plug y into my inverse function, I get out x. Sometimes I think it's better if they use a and b, but I want to use the same notation your book uses, so if you want to read in your book, you can follow through with that. Okay, so is everyone okay with this? This is saying, I'm calling this inverse function, I want to call it x. I'm calling the original function y. Now, if I differentiate this function with respect to y, that would be finding the derivative of this side, right? But I don't know what the derivative of this side is, so I'm going to use this function, and then once I have it, I'm going to plug it back in, and we'll get the general formula. Okay, so if I differentiate this with respect to x, I get 1 equals the derivative with respect to x of f inverse of y. Right? So, let's say I get 1. Okay. So, what do I want to do? Okay, I switched this, and that was my problem. Generally, we say y is a function of x, right? So let's just forget this for a minute. And let's go. I'm going to switch what I call x and what I call y. So I'm going to say y equals f inverse of x, and x equals f of y. Knew it looked too easy. Okay. So now I'm calling y f inverse of x, and I'm calling x f of y. Generally, we think it the other way, like I just did, but your book switches the role of x and y. So if I put in y to my function, y is just a placeholder. It's a value. I put in a number y, I get out a number x. If I put in number x to my inverse function, I get out a number y. So is everyone okay with that? So sorry about the confusion before. So doing it the other way, I don't get anywhere. But doing it this way, I can't differentiate this function because I don't know what the derivative of the inverse is. That's what I'm trying to find. So if I differentiate this relationship, so the derivative with respect to x would be 1 equals the derivative of the outside evaluated at the inside times the derivative of the inside. Right? Do you notice I get dy dx? dy dx is exactly what I want to find. I want to find the derivative of y with respect to x. So I get dy over dx is 1 over f inverse of y. But y is this inverse function. So it turns out the formula is 1 over f, the derivative of f, evaluated at the inverse of x. So the here, because that's the derivative of the inside. This is some function of y. If I differentiate it, I differentiate the outside, but I evaluate it at y times the derivative of y. Does that make sense? So then I get dy dx. So this is what, again, I have dy dx, well, I want to call it what it actually is. This is saying the derivative of an inverse function equals 1 over the derivative of the original function, but you plug in the value of y. Right? This is a number. This is y of the original function. So let's look at an example, and I think it will click. This is the formula. We showed it by doing implicit differentiation. Let's look at example number 2. I have the formula f of x equals f of 5 plus x plus 1, and I want to find, so find f inverse of x, so find the derivative of the inverse function. Can I find the inverse function? I can't. I can't have x equals y to the 5th plus y plus 1 and solve for y by itself. Right? There's sometimes where it's impossible to get y isolated. We talked about implicit and explicit relationships, and it turns out this one I can't solve for y by itself. When I switch the roles of x and y, I can't solve for y by itself. So to find the derivative of the inverse, I can use the formula, and when I use the formula, instead of plugging in the x value, you actually plug in the y value. And so naming it x and naming it y can be kind of confusing. So the formula here for f inverse of x prime is going to be 1 over the derivative of the function evaluated at the inverse, but I'm going to call that y. So it turns out I have 1 over 5y to the 4th plus 1. Oops.
Why do you call it y?
Because y is the output of my...
I mean, why do you make them y's then? Because it's y equals
Yeah.
x to the 5th plus x, so why don't they say x?
Because I'm not looking for the derivative of the function, I'm looking for the derivative of the inverse. So remember when I say I plug in 2 to my original function, but I'm talking about the derivative at 1. Does that make sense? So typically we call x comma y. So if I plug in x to my original function, I get out y. So that's what I'm plugging into my inverse function. So I want to evaluate that at a y point. At where I plug in x to the function, I get out y. I'm evaluating this at y. Question?
One where you are finding the derivative of the inverse, basically the roles of x and y are switched.
Kind of, yes. So let's look at, okay. So if I want to find f inverse of 1, and I want to find the derivative of that. Question?
Hold on, what's the 5y to the 4th plus 1?
Yeah, plus 1. Let me rewrite that. 1 over 5y to the 4th plus 1.
So you're just finding the derivative of the first one, but instead of making it x, you make it y.
Yes. So the trick here is when it comes down to this 1. This is an x value. This is an x value. But my formula is 1 over 5y to the 4th plus 1, and I want to evaluate that at x equals 1, but plugging in x equals 1 doesn't get me where I have to find the y value. What is the y value? Right, they're related. If I plug in x to my original function, I get out y. But if I plug y into my original function, I get out x.
So do you have to use 3?
It's not actually 3. It's plugging in, and this is where it gets confusing when you're switching the role of x and y. So
Do you want to plug it into the bridge?
this is actually, it's not the x value, it's the f of x value, right? So this is the f of x value. F of x equals 1. So what is y going to equal? So you set 1 equal to x to the 5th plus x plus 1. So this is where I get crazy that they use x and y, and then they switch the role of x and y in the middle of the problem, so then x actually equals y. Yeah, you can. Yeah, let's see here. So they call y the inverse function, so we can obtain the equation f of y equals 1. So yeah, you're looking for, let's look at it in terms of a and b. So here I'm looking for the inverse at x equals a, so that tells me f inverse of a equals x. I shouldn't use x, I should use b. Let's use b for a minute. So that means f of b equals a. So if I plug b, which is given, sorry, b is what I want to find, into my original function, I get out a, and a is given. Right? Because a is the x point of my original function, which would be the y point of my inverse function. But we called the inverse function y. So when you're given a problem like this, you're going to set the x value, which is actually the y value, equal to your function and solve for the input value or the output value of your function. Make sense? No, it doesn't.
The function is f of y, you solve for the x. And if your function
Yes.
is f of x, you solve for y.
Yes, but then they will give you at a point. So find at x equals 1. But the x equals 1 is the y value of the original function. Does that make sense? Sometimes if you pull up the picture, your book's saying, okay, I want to find the derivative of the function at 2, but really that is finding the derivative of the inverse function at 1. So if I plug 2 into my function, I get out 1. So a lot of times the 1's going to be given. So you say, well, what am I plugging in my original function to get 1? Well, in the case of this example, I plug in my original function to get 1. I'm plugging in 0. So I plug in y. Your book still uses the notation here, this x equals 1. But x equals 1 means y equals 0. Because it's saying, but do you see how that gets confusing? Because a lot of times students will want to plug it back into the original function that's given as x equals 1 and plug in 3. But you're really plugging it back into, so that might be a good approach, is to write the inverse function in terms of y. So really you can say x equals y to the 5th plus y plus 1. And then they give you x equals 1, so therefore y equals 0. Okay, so let's do the one that's on Wiley and see if there's another example in the book.
So is that one equation you have circled there? Is that like the equation we use?
Yeah, this is the equation that you're always going to use, but you want to be careful here.
Switching Y's makes more sense. It makes more sense that way,
Here,
because that's
yeah,
kinda like
I think that
inverse
definitely,
anyway.
yes, I think that definitely helps. So let's look at another example. This example is in your book. It's the answer is actually 1. Okay, so let's look at this example again. Okay, so let's look at the same example. I think this will help clarify. Okay, so f of x equals x to the 5th plus x plus 1. So I can write that as x equals y to the 5th plus y plus 1. Does everyone understand that? That's like the first step in finding the inverse.
Is it f of y? So you have f of x and then f of y below that?
F of y would mean you have a function of y. This, you could name this y, because a lot of times we do that, right? We say y equals f of x. So we just name this y. So a lot of times, yeah, it has meanings with input and output. Okay, so here, if this would be my relationship for my inverse function. So if I want to find the inverse function, the inverse function's derivative, I'm going to take 1 over the derivative of x with respect to y. So the derivative of x with respect to y. So in this case, I get 1 over 5y to the 4th plus 1. Does everyone understand that? You feel like you could do that? So then my next step, if I want to evaluate this at x equals 1, I plug that back into this equation and find out then y would have to be 0. So we end up with the slope at x equals 1 and y equals 0 is 1 over 5, 0 to the 4th plus 1, which would be 1. Does that make more sense? I think, so this here seems to be key. Rewriting the function as a function of y.
How did you determine that y is 0?
Because I plugged x in here, so I have 1 equals y to the 5th plus y plus 1. So y is going to be 0 to get 1 equals 1.
So you just manipulate it according to what you want.
Well, they gave me x equals 1, and I said, well, what y satisfies x equals 1 in this relationship? So what this means is, if I plug 0 into my original function, I get 1. If I plug 1 into this function, I get 0. So these are, but I don't know what this function is, because I haven't written out the inverse explicitly. I still don't know what it is, but I can find the slope of the inverse by using this technique.
Okay.
Question?
So if the answer isn't as easy as 1 or 0, how do you solve for it?
It's yeah, it'll be pretty straightforward where you might need to rearrange equation on one side and square root it or something. But yeah. And we can find the derivative of an inverse without actually taking the inverse. And then we can also find the derivative of the inverse by taking the inverse and differentiating. So sometimes you can check yourself both ways there. Okay, so,
Sorry.
yes.
So you, once you write that out, you were plugging in 0 into the inverse.
Here I'm plugging in the 0 into the derivative of the inverse. To find the 0, I plug x into this relationship for x and solve for y.
So you have to do that first.
Yes, to find what the y value is. Because if I'm trying to find x in here, I don't have any x values to plug that into. So I need to find what x is, what y is, this relationship.
So how did you, did they give you x?
They gave me x. So I was asked to find the derivative of this function at 1, x equals 1. So that means I'm going to plug in 0 to the derivative of the function to find the value. Okay. So, sorry to get kind of caught up on that, but I think if you write this step out, you guys will be okay. Question?
Yeah, so when they say the derivative,
Of the inverse.
you end up all the way over there at 1.
Well, because this is the slope at x equals 1, y equals 0. So this is the value of the derivative at x equals 1, which is really plugging 0 into the function here. So they might write it like this. F inverse of 1, the derivative of that is going to be 1. But to find that, I'm not plugging 1 into my function. I'm plugging in 0 to my function. Okay, so the next thing we're going to look at is the exponential functions. So your book shows this by doing the same trick. They say, let's call x log base b of y, and let's call y b to the x. So these are two functions that are inverses of each other, right? I call one x and I call the other one y. And if I differentiate this function with respect to x, I get 1 equals log base b of y is 1 over ln of b times 1 over y times dy dx, right? dy dx is the derivative of b to the x. So if I solve for dy dx, I get ln of b times y. But y is this function, so I get ln of b times b to the x. The derivation is not too long, but I'm not going to ask you to do it. I'm going to ask you to apply. So it turns out here we can write the derivative with respect to x of a function that's like b to the x is ln of b times b to the x. So let's look at what would the derivative of e to the x be. What's ln of e? ln of e is 1. So it turns out here this is just e to the x. So this is just another point where we can favor ln of x and e to the x over any other base. But now that we know this, we can use it. So let's look at some examples. What is the derivative with respect to x of 2 to the x? Very good. It's ln of 2 times 2 to the x. ln of 2 is just a number.
You want the number or
ln
ln of 2?
of 2. On the exam, it will say like use exact numbers. ln of 2 is the exact number. ln of 2 is irrational decimal. So, okay, what's the derivative with respect to x of e to the cosine of x? This is a chain rule. What's the derivative of e to a power? E to that power times the derivative of that power. So I can say if u is a function of x, then the derivative with respect to x of e to the u is e to the u times du dx. Right? So in this case, I would have e to the cosine times minus sine of x. Right? Minus sine of x, e to the cosine of x. You guys see that? E to the power, the derivative of e to the power, is e to that power times the derivative of the power. So you might have something like, what is e to the x times cosine of x? Question?
I have a quick question. Can you still put that e to the cosine of x into the original ln of e?
You can. You can do logarithmic differentiation and pull that down. And I can do an example of that. I'll do an example and show you it's going to be the same thing. So what is going to be the derivative of e to the x times cosine x? Very good. E to the x cosine of x, right? That doesn't change. Times the derivative of the inside, which would be cosine of x plus minus x sine of x. So this would be the whole answer. You guys see that? Derivative. This is a chain rule. The outside is e to a power. The inside is the power. So the derivative of e to a power is e to the power. So that stays the same. Times the derivative of the inside. Well, the derivative of x is 1, so whole cosine, plus the derivative of cosine is minus sine, and hold the x. So I just wrote that a little nicer.
Sorry, the fourth example, why do we use the ln?
The ln, because the formula. So let's look at y equals 2 to the x. So let's say y equals 2 to the x. So let's do logarithmic differentiation. So I have ln of y equals ln of 2 to the x, right? So I can rewrite this as ln of y equals x times ln of 2. Then I can differentiate this with respect to x. What's the derivative of ln of y? 1 over y times dy dx, right? Equals, what's the derivative of x ln of 2? ln of 2, right? The derivative of x is 1. We have ln of 2 is just a number. So if I solve for dy dx, I have ln of 2 times y. But what is y? 2 to the x, right? So this is ln of 2 times 2 to the x. That's kind of the long derivation of it. But you don't have to go through those motions. You can know the derivative of b to the x is ln of b times b to the x. And in the case when b is e, ln of e is 1. So the derivative of e to the x is simply e to the x. Okay, so when we have an example of a function that's u to the v power, where u and v are non-constant functions, you're going to use logarithmic differentiation Oh, sorry. So let's look at an example. Y equals x squared plus 1 to the sine of x. dy over dx does not equal sine of x to the x squared plus 1 sine of x minus 1 times 2x. Don't do that. That's the power rule only works when your power is a number, not a function, right? So the only way to do this problem is logarithmic differentiation. When you take the ln of both sides, you can take that power down as a coefficient and then deal with the product rule and then solve for dy dx. All right? So if we go through this, I have ln of y equals sine of x times ln of x squared plus 1. Does anyone have any questions on that step? If I take the ln of this side, I can bring this out front, and so I have sine of x ln of x squared plus 1. So now, I take the derivative with respect to x. What's the derivative of ln of y with respect to x? Good. 1 over y times dy dx. Then the derivative of the right-hand side is the product rule. The derivative of sine, hold the ln function, times the derivative of the ln function, hold sine. So I have cosine of x, ln of x squared plus 1, plus sine of x, 1 over x squared plus 1 times 2x. Right? So if I solve for dy dx, multiplied by y. But y is a function of x, and we have that right here. So I write dy dx equals cosine of x ln of x squared plus 1 plus 2x sine of x over x squared plus 1, all multiplied by x squared plus 1 to the sine of x. And this is your answer. So the derivative of ln of x squared plus 1, the ln function is 1 over, right?
Oh, okay.
So I have 1 over evaluated at the inside, hence the derivative inside. So you guys see that? So the last thing we're going to talk about is derivative of inverse trig functions. So we're going to do, so if I want to find the derivative with respect to x of sine inverse of x, then I have a relationship to my original function, sine of x. So I'm going to say, let's let y equal sine inverse of x. So x would then be sine of y. The same process, right? I call y the function I want to find the derivative of, and I call x my original function as a function of y. So now if I differentiate this function, I get 1 equals, what's the derivative of sine of y with respect to x? Right? So here, if I solve for dy dx, I have 1 over cosine of y. But what is y? Sine inverse of x. So the derivative with respect to y, the derivative of y with respect to x is 1 over cosine of sine inverse of x, right? Which is exactly what our formula says. Right? Our formula says 1 over the derivative of the original function evaluated at the inverse function. Right? Than we did before. You can always show that by going through the motions. So the identity your book gives you, so if this angle is sine inverse of x, we have the relationship x 1 minus x squared, right? If I have this relationship sine inverse of x equals y, I get, so sine of this angle is x over 1, right? Because sine inverse of sine cancels out the signs, you get x. So sine of this angle is x over 1, and so then I can find the missing piece by using Pythagorean's theorem. So I get this relationship. You guys see where that comes from? Because sine inverse of this angle has to be x. So this has to be x over 1. So I get this relationship. So what is the derivative with respect to x of sine inverse of x? Well, that's going to be 1 over cosine of this angle. What's cosine of this angle? Right, I have 1 over cosine. Cosine would be adjacent over hypotenuse. Hypotenuse 1. So I get this formula. Question?
How did you get the x equals sine y at the top after you said let y equals sine?
I name them. So a common thing in this is to name the inverse function y because you want to find dy dx. And then you always get the x function is the inverse of the inverse, which is the original function. So if y is sine inverse of x, then x is sine of y. Because these are the relationship between the function and the inverse function. Okay? So since I have the relationship sine inverse of x, if I take sine of sine inverse of x, I have to get x. So I know this is x over 1, and then I can find this missing piece by doing Pythagorean's theorem. So I get this relationship, this identity. So when I want to find the the derivative of the inverse, that's 1 over cosine of the angle. So cosine of the angle is the square root of 1 minus x squared over 1. So I get 1 over that. Cosine, secant, tangent, cosecant, and cotangent all can be done in the same manner. So we ran out of time, so on page, I think it is 201, you can find the others. I will answer any questions on Wiley on Monday. I might pull up a few and do some examples. If not, I will see you guys. If you don't have any questions, I'll see you guys on Monday.